Hello, everyone. Welcome to the 100th online Spintronics seminar. Thank you for your continuous support. It is my great pleasure to introduce today's speaker. Dr. Arnab Bose completed his PhD in the year 2018 from Department of Electrical Engineering, IIT Bombay, India, under supervision of Professor Ashwin Tulapurkar. He worked in the field of spin-orbit torques and spin caloritronics during his PhD. Then after, he joined Cornell University as a postdoc, working in the group of Professor Robert Berman and Professor Dan Rolfe, exploring the unconventional spin current generation by the single crystal materials such as iridium oxide and ruthenium oxide. He moved to Matthias Clauey's group at the University of Mainz, Germany, in the year of 2021, working in various areas of spintronics. So without further ado, Arnab, you have the floor.
Thank you so much for the nice introduction and giving me the opportunity to present our research in this platform. It is incredible that this online Spintronics seminar has stepped into 100th episode, which is really awesome, and it has become now one of the greatest platform to learn Spintronics online. Thank you so much for the opportunity to present. Today, I'll talk about the generation of tilted spin current by the collinear antiferromagnet ruthenium dioxide. This work was done when I did my postdoc at Cornell University. This work was possible due to collaboration among different groups, and this work was supervised by Professor Dan Rolfe. My another postdoctoral supervisor, Professor Robert Berman, unfortunately passed away last year. He could not see the outcomes of this result of this work. So I would like to present this seminar in his memory. Outline of my presentation is the following. First, I start with the background and motivation for our research. Here, mainly, I'll discuss the conventional and unconventional spin current. Then I'll talk about the measurement techniques, discussing two main techniques, Sdfmr, spin torque ferromagnetic resonance, and in-plane second harmonic Hall. Then I'll talk about the band structure of ruthenium dioxide, the recent predictions of spin split bands that would lead various exotic electronic transport properties. And after that, I'll talk about the experimental detection of the tilted spin current in the MB-grown epitaxial, very high quality ruthenium dioxide thin films. So let me start with the brief discussion of spin orbit torques. For the spin orbit torques, we need a source of spin current. One of the ways to generate efficient spin current is by spin Hall effect. For this, we need a heavy metal. When we run in-plane current in the heavy metal, or when we apply in-plane longitudinal electric field, it creates transverse spin current, where the spins are polarized perpendicular to the direction of both electric current and the spin flow direction. Now, when we have an adjacent magnet, it absorbs this spin current, and it experiences damping like and field like torques. Now, if we have very large spin current density, more than a critical value, then we can switch the polarity of the magnetization of the free magnet. And the state of the magnetization of the free magnet can be measured by reading TMR in the MTJ fabricated on this heavy metal. This has been reported in this pioneer work. Instead of having an in-plane magnet, we can also have out-of-plane magnet on the heavy metal. This is particularly very interesting for the high-density memory applications. Here, we see that the accumulated spins from spin Hall effect are perpendicular to the direction of the PMA magnet. So it cannot produce very efficient spin orbit torque for the field-free switching or for the deterministic switching. However, we can do some tricks. For example, we can apply in-plane external magnetic field that will tilt the PMA magnet a bit, and then spin orbit torque can be activated and it can switch. This has been reported in this pioneer works. In this case, only a single ferromagnetic layer is enough for the reading. For example, the magnetic state can be read by the anomalous Hall effect. Here, we see that already we need to do some tricks, for example, applying external field or exchange bias to achieve deterministic switching. So ideally, we would require this sort of case where in-plane electric field or in-plane current can generate out-of-plane spins flowing in the out-of-plane direction. Then these spins can directly produce out-of-plane antidamping torque on the adjacent magnet, and it can produce a very efficient spin orbit torque-based switching. So the generation of out-of-plane spins from in-plane current that flows in the out-of-plane direction, I call this unconventional spin current that produces out-of-plane damping-like torque. Now, naturally, the question is, in what materials we expect this sort of extraordinary spin current? Let's consider this case. And let's assume that when we apply in-plane electric current in this material, it produces out-of-plane spins. Now, upon taking the mirror reflection, we see that the generated spins flip the polarity because it is pseudo-vector. That means it will naturally be not possible in most of the polycrystalline materials. So it would be then allowed in various single crystal materials when we have mirror symmetry broken perpendicular to the direction of the applied electric current. This has been reported for the first time in tungsten ditelluride, and also recently in different materials such as single crystal copper platinum. But this is not the only way that we can break the symmetry. For example, we can have magnetic ordering in the system that also breaks the symmetry. So depending on the direction of magnetization, we can also have this sort of exotic spin current, which is also referred as magnetic spin Hall effect. Sometimes the spin current is also generated at the interface of ferromagnet and the non-magnet, very nicely summarized in this review article. Also, for more details, you can refer to the previous presentation given by Vivek Amin in this online Spintronics seminar platform. However, in this talk, I just give you a couple of examples. In one case, we have this sort of magnetic trilayers. We have in-plane magnet and out-of-plane magnet separated by a non-magnetic spacer. So this in-plane magnet is the source of spin current, and this is the detector. When we run the current, it creates out-of-plane spins that produces out-of-plane antidamping torque on the perpendicular magnet. This has been reported in this work. In one of my experiments, we also did very similar things. We also implemented in-plane GMR, but we had both magnets in the plane. One of the magnet was pinned using the ferromagnet antiferromagnetic standard coupling. In this case, we find that when we run the in-plane electric field or in-plane current, it produces an effective out-of-plane magnetic field that causes in-plane torque on the magnet. So both these methods can be very efficient to manipulate out-of-plane spins. In this case, however, we tried to pin the magnet or pin the spin source. Still, it can be susceptible to external magnetic field perturbation. So ideally, we will need a spin source which is very robust, such as platinum, but at the same time, we need the magnetic ordering. This can simultaneously fulfilled if we have an antiferromagnet that we'll see in the later part of this talk. Now, let me explain what are the different types of spin orbit torques that can be present and how to detect them. Here I show you three different types of spin current when in-plane current is applied in a non-magnet or even a ferromagnet. The first one is very common to us, that is from the spin Hall effect, where we know the accumulated spins are perpendicular to the direction of the electric field and flows out of the plane. We can also have this situation where the accumulated spins are polarized along the direction of the electric field. This typically happens in the systems where we have Dressel house-like interaction. The third possibility is that we can have a generation of out-of-plane spins flowing in the out-of-plane direction. This is referred as unconventional spin current, reported in some of the single crystal materials. Now, if we have an adjacent magnet that can absorb the spin current and it can experience 6 different types of torques, 3 different types of damping-like torques and 3 different types of field-like torques. Now, by looking at the different types of torques, we can exactly know what type of spin current is generated. So we need to know experimentally how to quantify and identify all these types of torques. So there are 2 standard methods. One is second harmonic Hall and another is Sdfmr. So let me first start with the second harmonic Hall. In the second harmonic Hall, we run low frequency AC current in the ferromagnet heavy metal bilayer. We measure DC voltage, we measure second harmonic Hall voltage by a standard lock-in measurement technique, while we rotate magnetic field in the plane. Due to various current-induced torques, magnet oscillate in the plane and out of the plane. It oscillates in the plane due to out-of-plane torques, and it oscillates out of plane due to the in-plane torques. And when it oscillates, its resistance also oscillates due to anomalous Hall effect and planar Hall effect. Now we have oscillatory resistance and oscillatory current, both mix up to produce second harmonic Hall voltage that we experimentally observe or experimentally measure, which will have a particular angular dependence with respect to the magnetic field that we apply or that we rotate. For example, if we have damping-like torques from the spin Hall effect, then it will have angular dependence of cos phi. If we have field-like torques, out-of-plane field-like torques from the standard Oersted field or Rajba-Edelstein effect, then the angular dependence would be cos pi, cos 2 phi. For example, if you have out-of-plane spins, and if that produces damping-like torque, meaning out-of-plane damping-like torque, then we'll have angular dependence of cos 2 phi, and so on and so forth. So the bottom line is, by fitting the experimentally measured second harmonic Hall voltage with these expressions, we can identify and quantify all different types of torques. Here, one important thing to note is that these coefficients also depend on the value on the magnitude of the applied field. And typically it goes down when you apply large magnitude of external field. This is how we can separate out the second harmonic Hall voltage that originates from the spin orbit torques from the thermal artifacts. Now, let me explain how Sdfmr works. For the Sdfmr, again, we have a heavy metal ferromagnet bilayers, but we pattern it to rectangular shape as shown here. And we make contacts of coplanar waveguide shape such that it can carry microwave current. So we run a radio frequency or microwave current in the system, measure DC voltage using bias T, while sweeping the external magnetic field at an angle phi with respect to the current flow direction. Due to various current-induced torques, the magnetization rotates, and here the resistance varies due to anisotropic magnetoresistance. Now, oscillatory resistance and oscillatory current again together mix up to produce DC voltage, and we can measure very large DC voltage at resonance as shown here. So this is a typical Sdfmr DC voltage spectrum. This can be fit using symmetric and anti-symmetric Lorentzian. From the symmetric Lorentzian, we'll get all the informations about in-plane torques. And for the anti-symmetric Lorentzian, we get all the informations about out-of-plane torques. Now we repeat the experiment for different values of phi to get the angular dependence of the symmetric and anti-symmetric components. From this angular dependence, again, we can identify and also quantify 6 different types of torques, 3 different types of damping-like torques and 3 different types of field-like torques. So these are the 2 techniques that I have implemented in this current study. Before jumping to the experimental results, let me discuss the band structure of ruthenium dioxide. First, let's start with the simple case of a ferromagnet, where we have non-zero magnetization. For the ferromagnet, we have magnetic ordering and global exchange field that creates the spin split bands, as shown here. So this is well standard. Now, let's consider a simple case of an antiferromagnet. Here, I have considered 2 different sublattices. One is upspin, another is topspin. So say this is the purple one is upspin and this one downspin. Now, after taking the space inversion, so green, because after taking the space inversion and the time reversal, we find this is PT symmetric. And the moment it is PT symmetric from the Kramer's theorem, it guarantees that it will have spin degenerate bands. And now, due to the local antiferromagnetic ordering or magnetic ordering, we'll have another sets of bands at higher energy level. But still, we cannot have spin non-degenerated bands as a function of K. So this is all standard for the regular collinear antiferromagnet. Now let's have a look what happens for the single crystal ruthenium dioxide that we are interested in. So this is a crystal structure of ruthenium dioxide. These are the non-magnetic oxygen atoms, and these are ruthenium atoms. So 2 sublattices, one is upspin, another is downspin, resulting net magnetization is 0. Now, if we ignore these oxygen atoms, non-magnetic oxygen atoms, then it exactly looks like this standard collinear antiferromagnet. But the moment we consider the non-magnetic oxygen atoms, it immediately breaks up PT symmetry. Rather, we have 90-degree rotational symmetry. So in this case, we cannot apply Kramer's theorem anymore. And this recent theory works predict that it will exhibit spin split bands in the band structure. That depends on the K, unlike the regular collinear antiferromagnets, even though the net magnetization is 0. Now, due to the local magnetic ordering, for the higher energy, we'll have alternate copies of this band. So it is also sometimes referred as altermagnet. So we'll see that this spin split bands will have tremendous influence in the electronic transport properties. For example, when we run electric current or electric field along certain crystal axis of ruthenium dioxide, it can create spin polarized current. And it is predicted to generate a GMR and TMR effect even in the antiferromagnetic junctions. In presence of the spin orbit coupling, it can also exhibit crystal axis dependent anomalous Hall effect as predicted here. The third possibility is that even in the absence of spin orbit coupling, it can still produce transverse spin current, just the way platinum creates transverse spin current from spin Hall effect. But this is fundamentally different than platinum, because for this case, we don't require any spin orbit coupling. The spin split bands are enough, and the spin split is so powerful, so large in this material, then we can have very strong pure transverse spin current, which will strongly depend on the direction of current flow with respect to crystal axis. And second difference from spin Hall effect is that here the generated spins will be parallel to the Néel's vector. Okay, now the question is, how do we experimentally detect this? So let's consider the single crystal ruthenium dioxide as shown here. So this is the 001 direction, and this is 001 plane. So the theory predicts that when we run in-plane current or in-plane field along this axis, 0, 1, 0 axis, then it creates transverse spin current along minus 1, 0, 0 axis, perpendicular to this. And spins are parallel to this Néel's vector. Now you may again think that it is similar to spin Hall effect, but it is completely different because for the spin Hall effect, we have spin current in all the planes. It goes up and it also goes sideways, unlike this case. Here, unlike this case, the reason is here, the direction of Néel's vector determines the polarization of spins. Now, we find that if this theory prediction is true, then it should create very different sort of spin current in another plane, which is 101 plane. This shaded blue area is 101 plane. Now, by rotating this with theta s along z-axis, we can get 101 plane here, and then this shaded area shows the 001 plane. So when we do the coordinate rotation, also we do the rotation of the spins. So naturally, in this plane, when we run current along 0, 1, 0 axis, we naturally get a tilted spin current. So this tilted spin current would be this tilted spin current is the one that we want to experimentally detect. For this, we patterned devices along different, such that we can apply current along different crystallographic directions, as shown here. We fabricated devices for the Sdfmr and second harmonic Hall measurements, as shown here. There are two important things to note. First is that here for the 101 plane, we have canted Néel's vector, meaning it will have projection of this Néel's vector in the plane and out of the plane. So this is a projection of the Néel's vector out of the plane. And now if we run current along certain crystal axis, for example, at an angle psi, then we'll have the further projections of the Néel's vector perpendicular to the direction of current and along the direction of current. Meaning in this plane, 101 plane, will have all x, y, and z component of spins. And this is what we want to experimentally measure. For that, we need to have a probe to detect the spin currents. We have permalloy on 101 oriented ruthenium dioxide. Previously, I discussed that this magnet absorbs spin current and it will experience torques. So these are we will measure different types of spin orbit torques as a function of crystallographic directions. So this magnet will experience spin torques from the y component, z component, and x component spins, as I discussed here. And importantly, they will have a specific angular dependence. For example, y component of spins will have cos square psi, z component should have cos psi, and x component should have sin 2 psi angular dependence. Let me explain a bit how. Let me explain a bit the derivation of this. There are three important points. First of all, in this sort of materials, always it is important in which direction we run current with respect to crystal axis. Here, theory predicts that it can generate it can generate this exotic spin current when we run current along 0, 1, 0 direction. And it will create 0 spin current when we apply in this direction. So it naturally creates cos psi angular dependence because of that. The second point is the generated spins would be parallel to the Néel's vector. So projection of the Néel's vector comes in the angular expression. So for example, for the z component, we have this cos theta. And for the y component, we have sin theta cos psi. And for the x component, we'll have sin theta sin psi. Now, the third projection is for the direction of the spin flow. Again, the theory predicts that when we run current along this direction, 0, 1, 0, then we'll have pure spin current transverse to this, which is minus 1, 0, 0. But however, we are not measuring spin current in this direction. Rather, we are measuring spin current in this direction that has an angle. That's why additional sin theta comes. So finally, the summary is In the 101 oriented ruthenium dioxide permalloy bilayer, if we measure spin orbit torques, we should see a clear angular dependence of different types of spin torques. The y component should have, again, I'm repeating, cos square. Z should component spin torque should have cos psi, and x component spin current or spin torque should have sin 2 psi. This is what we want to experimentally measure as a probe for the spin speed bands of ruthenium dioxide. Now, let me show you some experimental data. First, let me discuss a couple of examples where we run current along 0, 1, 0 direction, which I refer psi equal to 0. And then I discuss when we run current along psi equal to 90 along this direction. Just to remind you, here we are doing Sdfmr, meaning we run RF current, measure DC voltage by sweeping external magnetic field at an angle phi. So here we get this sort of Sdfmr voltage spectrum that is fed to symmetric and antisymmetric Lorentzian. And now for a given crystallographic direction, we do the measurement for different values of phi to get the angular dependence of the symmetric and antisymmetric component. Here, I have shown that when we run current along this direction, psi equal to 0, there is a clear difference in the symmetric and the antisymmetric components. The symmetric component has cos phi, sin 2 phi angular dependence that originates from the regular spin Hall effect. However, for the antisymmetric component, the difference is due to this extra term, that is sin 2 psi. That clearly suggests that we have out of plane spins generating from the in-plane current in this direction that flows out of the plane. And on top of that, we have regular cos psi angular dependence that leads to this angular dependence in the antisymmetric component. In contrast, when we do the measurement for this direction, psi equal to 90, we find everything is standard. Both symmetric and antisymmetric components show the angular dependence cos phi, sin 2 phi, meaning here we have regular spin Hall effect, and here we have a regular Oersted field. We also want to verify this by doing another experimental technique, which is an independent study, that is a second harmonic Hall measurement. Just to remind you, for this, we pattern Hall bar as shown here, measure second harmonic Hall voltage by rotating in-plane magnetic field. This is a typical second harmonic Hall voltage spectrum that you see. First thing that we notice is the clear difference, clear angular difference in the second harmonic Hall voltage when we run current along psi equal to 0 and psi equal to 90 as shown here. The difference is due to this extra term. For the psi equal to 90, we have the standard damping like torque from the regular spin Hall effect, the cos phi angular dependence, and on top of that we have components from the Oersted field, which is cos phi, cos 2 phi. But here, on top of these two, we have this additional term that strongly suggests that we have out of plane spins generating when we run current in this crystal axis. So finally, the summary of this slide is we did two independent measurements which are in agreement, and they strongly suggest that we have very strong crystal axis dependent generation of extraordinary spin current. Now, instead of doing only these two angles, we measured spin orbit torques for other angles, 30, 45, 60, 90, and so on. Let me show you the data for that. Here, we quantify the damping lag torque efficiency for the Y polarized spin. This is for the Z polarized spin, and this is for the X polarized spin. For the Y polarized spin, the damping lag torque is proportional to cos square psi. The Z polarized spins, it is proportional to cos psi, and for the X polarized spin, it is proportional to sin 2 psi. This is a very good agreement with the theoretical predictions that I discussed before. So this clearly suggests that we have tilted spin current generating in the 101 ruthenium dioxide film that strongly depends on the direction of current flow with respect to crystal axis. One important thing to note that here we have offset in the Y polarized spins. This offset indicates that on top of this extraordinary spin current, we have regular spin Hall effect. That spin Hall effect would even exist if there is no magnetic ordering. However, this specific angular dependence strongly suggests that it originates from the novel spin split bands of the emerging new type of antiferromagnet ruthenium dioxide. So recently, we find that similar work is also reported in this archive paper. They have also observed similar angular dependence for ruthenium dioxide. There is a recent work here. Their approach is different, but still the final conclusion is same. They also show the evidence of spin split bands in the transport measurements through spin orbit torque studies. In the last year, we find that there was a report of spin orbit torques in manganese to gold. However, in that case, the antiferromagnetic spin Hall effect that we talk about here is different from them, because here the spins are polarized along the direction of Néel's vector, unlike in that study. So this is fundamentally different than what we are reporting here. So we also did some other control experiments. For example, we did similar studies on 101 oriented iridium dioxide thin films and permalloy bilayers. We run current in the same direction, but we don't see any extraordinary spin orbit torques in iridium dioxide. We studied iridium dioxide because iridium dioxide is isostructural as compared to ruthenium dioxide. Both are rutile oxides, and their lattice constants are nearly same. So it clearly suggests that only crystal structure and crystal symmetry is not enough for these extraordinary spin currents. We need this magnetic ordering that ruthenium dioxide exhibits, but not iridium dioxide. However, this iridium dioxide is also very interesting material because it also hosts Dirac nodal lines that can create an isotropic spin Hall effect, which we reported in our previous works. For more details, you can check out this paper. Okay, so we also measured spin orbit torques in other planes of ruthenium dioxide, for example, 001. In 001 plane, we also don't observe any extraordinary spin torques or spin currents, which is also theoretically, which is in agreement with the theory. That means, again, there is a strong crystal axis dependent extraordinary spin orbit torque, not only crystal axis, but also crystal planes. The third thing is we inserted spacer between the source and the detector. We inserted iridium as spacer. In this case, we found that the angular dependence, the extraordinary spin torques have gone down, but still it is present. It is non-zero. But its magnitude has gone down because of the spin attenuation through the iridium that has small spin diffusion length, suggesting that it is bulk in origin. The next thing that we did, we varied the thickness of the heavy metal, which is ruthenium dioxide here. And we find that as we increase the thickness of ruthenium dioxide, spin torque increases. And finally, it will saturate. Again, this suggests that the spin current that we report here originates from the bulk bands of the ruthenium dioxide. The last thing that we did is a temperature-dependent measurement of this. Particularly, we quantified the out-of-plane antidamping torque in these two crystal directions as a function of temperature. In this -101 direction, we do not observe any out-of-plane antidamping torque at any temperature. But for the 010 direction, it has very strong temperature dependence. It nearly increases by 200%. So this strongly suggests that we have time-odd spin current generating from ruthenium dioxide as theoretically predicted. This is, again, in contrast with the regular spin Hall effect that generates from the spin Hall effect. Because in that case, if the origin is the spin pericurvature and within the intrinsic limit, we do not expect very strong temperature dependence, unlike this case. So all this together are in agreement with the theoretical predictions of the spin split bands of ruthenium dioxide that could lead very extraordinary spin current. So in summary, we have measured spin orbit torques in very high quality epitaxially grown ruthenium dioxide single crystal thin film permalloy bilayers. We observe strong crystal axis dependent extraordinary spin current or tilted spin current that originates from the spin split bands of ruthenium dioxide as recently been predicted. So with this, I like to conclude my talk by acknowledging several people. Harinaar, Néel, they grew ruthenium dioxide thin films under the supervision of Professor Shlom. And Jackson and Josein grew the iridium dioxide thin films. They're from Material Science Department, Cornell University. We also got a lot of help from our collaborators, Ding Fu and Professor Simbol. Their DFT calculations really helped us a lot for this work. Xue Zhang, working under Professor Muller, did the STM imaging. That was very helpful. Rakshit Jain did the low temperature out of plane antidamping measurements and contributed to the understanding of the spin current generation. That was very helpful. This work was supervised by Professor Dan Wolf, and we are very thankful for Professor Robert Berman. He was my postdoctoral supervisor. Unfortunately, he passed away, but his contribution to Spintronics is immense. Finally, I like to thank my funding agencies and Cornell Nanofabrication Facility and CCMR that helped this work. Yeah. So with this, I like to conclude my talk, and now I'm happy to take questions if you have.
Thank you very much for this interesting talk. We can use the reaction button to thank the speaker. If you're watching this on Zoom and have questions, please use the raise hand function, or type your questions in the chat box. I can read it for you. And if you're watching this on Twitch, you can also type your questions in the chat box. While we're waiting for questions, I see there are 2 questions in the chat on Zoom. So the first one is, can I expect out-of-plane spin current in amorphous state materials? Can you comment on this?
So my understanding is that is most likely not possible. It has to be either single crystal material, or we need magnetic ordering. If it's a magnetic material, then we can have out-of-plane anti-damping torques or extraordinary spin currents even for the polycrystalline material. But that may not necessarily exhibit the sort of angular dependence that we observe in this particular material.
Thank you. The follow-up question is, a different question is, if spin current generation, it depends on the crystal axis orientation, does it mean that the materials has different spin splitting at different axes?
So let me show this. This is the Fermi surface that we see, and when we apply electric current in this direction, it moves Fermi surface such that it naturally creates transverse spin current in this direction. When we run current in this 0, 1, 0 axis, which is schematically shown here. When we run current in this direction, it naturally creates transverse spin current, but it doesn't create transverse spin current in other direction as compared to platinum. Now, if it creates transverse spin current in this direction, then if we want to measure the spin current in other plane, then we need to do the coordinate rotation as shown here. So which will naturally lead to the tilted spin current as shown here. So my answer to your question is that it has a particular type of spin split bands as shown here. And for the more details, you can check out these theory papers, but the Fermi surface will look like this.
Thank you very much. Do you have other questions? Oh, quick question. So, well, have you showed that the electric conductivity of ruthenium oxide?
Mm-hmm. Sorry.
What is the electric conductivity of ruthenium oxide?
Okay. I can give you the resistivity. The resistivity of ruthenium dioxide was around 140 micron centimeter for 101 plane.
140 microohm centimeter. I see. Thank you. So in terms of, if I call this as the effective spin Hall angle, it's not that large.
Yeah, so let me, yes, so it is not extremely large. I would say it is nearly 1 order magnitude smaller than platinum.
I see.
Yeah, but still, yeah.
Sure. Thank you.
So one of the possibilities, yeah, please go ahead.
No, continue us.
Okay, so one of the possibilities that we think could be due to the domain cancellation, because here the origin is the time odd spin current. So if it is in the multi-domain state, then we'll have reduction of the spin current. That's why probably we have nearly 1 order magnitude lower reported value of spin current than the theory predictions. But that is one of the possibilities.
Thank you. And actually, that's exactly to the follow-up question I want to ask. If it is related to the Néel order, are you able to control the Néel order to change the spin current that generated? You can flip that, or?
Unfortunately, that experiment we didn't do, because what we found in the literature that we require around 35 Tesla field to flip the Néel's vector that we didn't have. And secondly, yeah, so that was the main thing. But here, at least we could run current along different axes, and still we can probe the different projections of the Néel's vector and to confirm how it affects.
I see. Yeah. Thank you. We have 2 more questions in chat. The first one is, what can be the potential applications in devices or memories of this tilted spin current?
Okay, thanks for this nice question. First of all, in the first slide, I have shown that the spin Hall effect is very good, but for spin Hall effect, we need extra symmetry breaking field here, extra symmetry breaking field just to tilt a magnet, or we need to do some other sort of tricks, for example, having an antiferromagnetic exchange bias to achieve deterministic field-free switching. So this sort of tilted spin current could be a potential way to generate out-of-plane anti-damping torques, and that could be interesting for the memory applications.
Thank you. And one more question. What is the spin diffusion length in this material, in this case?
Okay, so exactly, I have not calculated it, but we did a bit thickness dependence of ruthenium dioxide. From that, we can speculate some number, but we have not done very detailed thickness dependence. It will be around 6 to 7 nanometers. Just I'm roughly speculating from this curve.
Okay, yeah. Thank you. Kirill, please go ahead and ask your question.
Yes, thank you. Very interesting talk. So I have a follow-up question regarding the domain structure. So when you measure the dependence on the crystallographic axes, for example, you need to have those devices fabricated in different places, so your domain structure there can be different. So how do you take that into account when you analyze the angular dependence?
So that's very interesting question. And yes, we could have different domain formation, domain structure around different angles, but here First of all, we did not image the domain configuration. So exactly we cannot say that whether it is and how much is the domain variant. But here our point is that if it was a single domain, then we would see this sort of angular dependence. And we just did the experiment and we found this angular dependence. And from that, we quantified the numbers. And what we found is that the spin torque efficiency is way smaller than the theoretical predictions. So that could be possibility of the domain cancellations. But to your question that devices are patterned along different places in the device, but I don't have any very clear-cut answer that why we have such a nice angular dependence. It seems that most of the devices have a similar sort of domain configurations.
But
Yeah, please.
Do you have one device per angle, or are you able to like accumulate some statistics like for a different for a given crystallographic orientation?
So that's a very good point. We definitely measured more than one devices, and of course there are thickness dependence. But yes, we have not measured like 20 devices and got statistics from this. So that's a very good point that could be done, and probably that can give us some information about the domain formation. We have not done it.
So I understand. Do you understand correctly that if you did that, you would expect to have, random amplitude centered at 0, sometimes positive, sometimes negative, with some range?
Yeah, I understand the point. Yes, I understand the point, but I don't know what will happen in that case. And also, we don't know. There could be possibility that because since we have ferromagnet adjacent to this antiferromagnet, there could be a ferromagnetic antiferromagnetic coupling, and that could stabilize essentially antiferromagnetic domain, preferably. So that can also happen. So more at Cornell, we are doing more research there to know exactly why we have such a nice angular dependence. But right now it is a bit puzzle. And also other possibility is that there could be time even spin current that can also contribute. Then it doesn't matter whether we have domain variants or not. We have also stated that in our paper. But the theory predictions are very low for the time even spin current component. So we think that is also quite unlikely to contribute completely on this angular dependence.
Thank you.
Okay, Rahul Gupta, please go ahead and unmute yourself and ask a question.
Hi. Can you hear me?
Yeah.
Yes.
Okay. Thank you for the nice talk, Arnab. I have a couple of questions. So first question is related to this titanium dioxide layer. So did you use this layer to grow the ruthenium oxide epitaxially, or what is the role of that layer?
Oh, titanium dioxide is a substrate. It is a single crystal substrate on which ruthenium dioxide is grown.
Oh, okay. And another question is related to the device size. So you measured these properties in Sdfmr using Sdfmr and also second harmonic measurement. So may I know what is the device size in both cases?
For the Sdfmr, I think the size we had is 20 cross 30 micrometer square, and for the second harmonic hall, probably the length was 20 micron and width was 6 micron, but in that range. I exactly don't remember, but it should be in that range.
Okay. Thank you.
Do you have other question? Let me just quickly check on Twitch. So looks like we have exhausted all the questions here. So if I have you want to do further discussions with Dr. Bose, you can feel free to stay. At this moment, we want to thank the speaker again, and I want to thank you all for participating.